Okay, we have pleasure today to have Snežana Lazić here at the Institute of Material Science in Barcelona, and she's working in the Autónoma University in Madrid from already many years. Snežana finished her PhD thesis at also in Universidad Autónoma in Madrid on optical characterization of semiconductors. After this, Snežana moved to University of Toronto in Canada, and after to Berlin in Paul Rudd institution. No? And in 2012, she got Ramon y Cajal. She incorporated to University of Autónoma in Madrid, and she started her research career in experimental photonics. And today she will explain us more about detection and of qubits, of phonon qubits, and in using the effects and different photonics structures. Yeah. Thank you very much.
So can you hear me well? Yeah, okay. So thank you very much, first of all, to Zorica and to Alberto for inviting me. It's my pleasure to be here. It's actually the first time after many years that I come to this campus. Well, I'm very happy to be here to share some part of our results that we do in our group. So as Zorica mentioned, I come from the Autónoma University in Madrid, and my group is in the Department of Physics of Materials. And the work that I will show today was a collaboration with researchers from the Polytechnic University, also in Madrid, and also departments of chemistry, condensed matter physics, and theoretical physics that also belong to the Autónoma University in Madrid. So what we did here is we used sound to dynamically in situ control quantum light that is emitted from different quantum states. And throughout this presentation, I will show two different examples of quantum systems that are quite interesting for future photonic quantum information technologies. So I basically work in quantum photonics. Because Alberto, I had the honor to visit some of the laboratories with Alberto before the presentation. And as far as I understand, the research here is not so much related to the quantum photonics. So for those of you who are not very familiar with the field, I would start before showing the results with a brief reminder of what quantum light emitters actually are. So there are different ways to distinguish between light sources, and one of them is to look at the temporal sequence of the emitted photons. So based on this criteria, we can distinguish classical or thermal sources, which, as you know, emit photons in bunches, and their counting distribution is much broader than the limiting sub-Poissonian distribution. Then we have coherent sources, such as lasers, with such random time intervals between the emitted photons, and they can be described by a non-deterministic Poissonian distribution. And what is of special interest to us in our group is the so-called non-classical, or also sometimes called anti-bunched quantum light, which basically emits such regular stream of photons, which, as you can see in this illustration, are emitted one at a time. They can be characterized by deterministic or sub-Poissonian distribution. And the reason why we are interested in such non-classical light is because we can manipulate this light at its fundamental single photon limit. And this means that we can use them to produce photonic qubits, like single photons that I will be focusing in this presentation, or entangled photon pairs. And those are essential for quantum communication information processing technologies, which are already taking us well beyond today's classical digital technologies. Now, examples of such some advanced applications in this area are, for example, quantum teleportation, quantum cryptography, enabling quantum internet, which is used for unconditionally secure transfer of information. And there's also quantum computing, which is capable of increasing computational processing power exponentially, as you know. And it is therefore capable of solving complex calculations that are not able to be solved by classical computers. So there are many candidates, so many physical systems that can be used to produce qubits. For quantum technologies, but we use photons because they have many advantages compared to other quantum systems, and some of them I show here, of these advantages I show here. So for example, they are well suited to be used as decoherence resistant qubits, which means that they are excellent carriers of quantum information, and this is basically because they only weakly interact with each other and with the environment. Now, also because of this weak interaction, they can be used to transmit information through optical fibers and also through free space. Then another important advantage of photons is that they have a number of degrees of freedom that we can use to encode information, like for example, polarization, optical path, arrival or emission time, which is also called time bin encoding, orbital angular momentum, then phase, wavelength, etc. And another important property is that typically we use semiconductor quantum systems to produce these photonic qubits, which are quite stable and robust, which is also important for practical implementation of quantum technologies. Now, the current quantum communication protocols today are mostly using polarization as a degree of freedom in order to convert qubits of information into different photon polarization orientations, like for example, as shown here, horizontal or vertical. However, this type of encoding suffers significantly from depolarization and decoherence issue, especially when the qubits are propagating to optical fibers. And this, of course, induces considerable losses that we would like to avoid in order to use them for quantum communication and information processing. So one way to overcome this limit is to encode information onto the photon emission or arrival time, so using this time bin encoding. And the advantage of this type of encoding is that it is much more robust in the sense that we can encode a large amount of information onto a single qubit. And this actually is among the most important functionalities in quantum communication and information processing. Now, let's see how do we actually generate single photons using solid state systems. So for that, we need to have a radiative recombination of charge carriers between two distinct, discrete quantum levels. So what we need actually is a two-level quantum mechanical system consisting of ground state and then excited states. So this system actually emits only one photon each time it is excited. So as a result, we get these anti-bunched photons as seen here. This means that the probability of having multiple photon emission per excitation cycle is basically practically eliminated. Now, these systems can be made in such a way that the recombining charges are either quantum confined in such localized potentials, like in quantum dots, for example, or they can be bound to the imperfections within the crystal lattice. Like, for example, we are talking about atomic defects here or chemical impurities. So in both ways, per excitation cycle, there will be emission of a single photon, and the energy of this photon will depend on the system. So in this case, it will be above the band gap, and here it will be well below the band gap energy. So I will discuss the cases, both cases throughout this presentation. So now the production of single photons is actually quite competitive research field. It has been for a decade now, and there were many solid-state systems that have been studied for this purpose, like, for example, atoms or organic molecules, or atomic defects in inorganic crystal, which include color centers, most known being nitrogen vacancy in diamond. And as of recently, atomic defects in two-dimensional layered materials such as TMDCs, hexagonal boron nitride, or other materials. One can also use semiconductor nanostructures such as epitaxially grown quantum dots. Now, here I will basically talk about these two systems because they are quite promising for on-chip production of quantum light. And this is mainly because of their scalability and their interoperability with the existing semiconductor technologies, especially silicon-based technology, which is currently mostly used. Compared to other conventional semiconductors, we focus on the 3 nitrides and 2D layered materials because they offer many advantages that are quite relevant for practical implementations of quantum communication and information processing. And here I list some of these advantages. In the case of 3 nitrides, because of their large exciton binding energy and band offsets, they are able to emit photons at room temperature. That's especially desirable for practical implementations, of course. Then they also cover a wide spectral band from deep ultraviolet for aluminum nitride to telecommunication wavelengths for indium nitride, therefore covering almost the entire solar spectrum. Now, what is of particular interest here are quantum emitters which are operating in the UV to visible, so here, spectral range. And this is because of their scalability and also because of the possibility of free space communication, so one doesn't have to use optical fibers anymore. Also, the specific valence band structure of Wurtzite 3 nitrides favors the emission of highly linearly polarized photons. And this is crucial for polarization encoded quantum protocols like previously mentioned quantum key distribution and linear optical quantum computing using photonic qubits. In the case of 2D materials, their main advantage is their low dimensionality, which basically provides them quite unique mechanical, electronic, and optical properties for applications in quantum photonics. So some of them are also shown here. So there's scalability, meaning that we can scale down these materials down to atomic, basically, layers. And because of this, quantum emitters based on these materials have exceptional brightness, more than the conventional semiconductors. Then also we can easily exfoliate thin layers or flakes from these materials and integrate them with other materials or structures on chip. So in this way, we can basically achieve on-chip heterostructuring simply by vertically stacking of different 2D layers, like in this illustration here. In addition, the band gap in these systems depends in most cases on the number of layers, and this can be used to tune the emission wavelength of the light. And also because of the strong exciton binding energies, we are talking about high temperature device operation, which can exceed by far room temperature. So all these advantages are very important for practical applications of these structures in quantum technologies. Even though there has been many research and very successful research in this field, there are still several challenges that we have to address in order to progress in this field. And one of these challenges is how to deterministically engineer quantum emitters at the nanoscale, which of course is relevant for integration of these emitters with other components for on-chip quantum information management. So one way to achieve such site-controlled emitters is, for example, by including quantum dots into micro or nanoscale heterostructures, like, for example, nanowires, as you can see here. Or what we can do also with 2D materials, we can use exfoliated flakes and place them on pre-patterned substrates, in which case we can achieve strain-engineered positioning of quantum emitters at specific locations. Now, another requirement that is very important for quantum technologies is to obtain indistinguishable photons, which means that they should have not only the same polarization and, of course, temporal and spatial extent, but also the same wavelength. And this, as you might know, is quite difficult to achieve in semiconductors. Therefore, it would be quite convenient to have some kind of in situ technique that would allow us to tune, so in real time, the emission wavelength of the photons. Because then we could easily realize quantum networks in the future. Another requirement is the on-demand production of single photons with controllable repetition rate at megahertz or even higher frequency range, which is still an issue for high-speed quantum information processing. So what is typically used to produce on-demand single photons are ultra-fast pulsed laser excitations. However, this method of excitation suffers from jitter in the photon emission time, and this is mainly due to the phase fluctuations within the laser pulses, even when they are operated in a mode lock regime. So it will be convenient to find another method that could suppress such jitter. There is yet additional challenge, and that is to control the optical polarization of the emitted photons, also in situ. And by controlling, I'm referring to both the degree of polarization as well as the orientation of the polarization axis. This is quite vital for, as I mentioned previously, polarization-encoded quantum information technologies, which are based on highly linearly polarized photons with deterministic orientation of the polarization axis. And now in most solid-state systems, control of the photon polarization state is not an easy task because it's either probabilistic or it is predetermined by the electronic properties of the system. So one example is shown here for the case of Birdside trinitride quantum dot, in which geometry of the system was engineered in such a way that the system emits photons with fixed orientation of the polarization axis. Because it is fixed, therefore we don't have here the capability for real-time control of the photon polarization properties. And this is, of course, not desirable for polarization encoded quantum communication. So basically, what I'm going to show here is that we will going to address some of these challenges that I mentioned in the previous transparencies. So what I'm going to show you here is that we can produce highly linearly polarized single photons using two different systems. So trinitride nanowire quantum dots, which are emitting in the UV to visible spectral range, and atomic defects in hexagonal boron nitride, which is a representative of 2D materials. And these defects are emitted in the visible to near infrared region. So I will first describe the samples and some of their structural and optical properties. And finally, I will give an experimental evidence of photon anti-batching from both of these systems. Then I will show that we can use the so-called surface acoustic waves in both of these systems in order to control in real time the photon emission wavelength to trigger the emission time of the photons, which is needed for on-demand production of single photons. We can also control the photon polarization degree and encode information into photon emission time. So let's start with the samples. So as for the three nitride structures that we are using, we are talking about nanowires here, and they were fabricated following the bottom-up approach by plasma-assisted molecular beam homoepitaxy using selective area growth technique, which we achieved by colloidal lithography. And as you can see in this scanning electron microscopy image here, the position of these nanowires is quite well organized on the substrate. And as you can also see, these nanowires exhibit such hexagonal cross-section with lateral facets defined by the nonpolar M plane. And they also show this pencil-like top profile which are defined by such semipolar S planes. Now, this is maybe going into details here, but bear with me because this designation of these planes is important, as I will show in this transparency. So the actual structure of our nanowires is a core shell, which means that there is a very thin indium gallium nitride layer, which is embedded inside of this gallium nitride nanowire. And as we could see, in transmission electron microscopy images recorded on individual nanowires, this intrawire InGaN nanoshell is formed on different crystallographic planes of both high and low polarity. So this includes this here or here, top polar facet. Then we have this upper semi-polar side facets, or this one here. And finally, we have such non-lateral here or here, non-polar facets. So what we have shown, in this publication here is that our nanowires actually first experimentally demonstrated nanostructures which are capable of simultaneously hosting quantum emitters with different crystallographic orientations. Now, as I will show later, all three sections of this InGaN nanoshell contain quantum dots, which are responsible for the emission of single photons. Now, the reason why it is necessary to have also the semipolar and the non-polar quantum dots is because the polarization-induced built-in field, which has a very strong value on for polar quantum dots, so these that are grown on this plane here, it does not exist in the case of non-polar and semipolar facets, or is significantly reduced. So what basically happens in polar quantum dots is because of the strong built-in electric field via quantum confined Stark effect, there is a significant spatial separation of the electron and hole wave functions, which essentially leads to the reduction of the phonon repetition rate. Therefore, it lowers the speed of the quantum devices. This, of course, doesn't happen in semipolar and non-polar quantum dots, where the recombination lifetime is much smaller, leading to much higher photon repetition rate. And therefore, with this, we can boost the operation speed of the quantum light devices. So as referring to two-dimensional layer semiconductors, we use the hexagonal boron nitride flakes. So we started with commercially available hexagonal boron nitride powder that we simply bought from Sigma Aldrich company. And these powders were in form of the grains of the diameter around 1 micrometer, as you can see in this scanning electron microscopy image, and they are with quite high purity. So now, in order to produce quantum light emitters inside these grains, so what we did is we thermally expanded them in argon atmosphere at around 1000 degrees Celsius for about 10 minutes. And this resulted in hexagonal boron nitride flakes, which are much thinner. So we are talking about thickness of 3 to 5 nanometers and the lateral dimensions of 2 to 300 nanometers, which we extracted from these AFM and TEM images here. Now, the atomic force microscopy characterization of HBN flakes also show that we have a presence of different vacancies, like 4-atom, single atom, or anti-site vacancies within our flakes. There are also other defects such as 2 or 9-atom vacancies or some other substitutional impurities, but those that I show here are the most frequently appearing in our flakes. Of course, the anti-site vacancy can be, for example, nitrogen or carbon related, in which case there is a nitrogen atom missing and the nearest boron site is substituted by either a nitrogen or a carbon atom. Using only atomic force microscopy, it is difficult to actually know what is the exact nature of each of these atoms. One has to combine it with high resolution transmission electromicroscopy. And if we compare our results to those which were published by other authors who also observe with a high resolution TEM, similar or the same defect structures, we basically come to the conclusion that what we have in our HBN flakes are multiple defect species. Now, we still don't know which exact defect is optically active. So that is still an open question in the community, and it's quite important to know that so that we can actually deterministically produce those defects that are producing single photon emitters. So now that I've described the samples, what we wanted to do is we wanted to find a way to control different properties of these systems in real time. And this can be done using strain and piezoelectric field of the acoustic wave that is propagating along the surface of some piezoelectric material. So in our case, we use such acoustic delay line, which consists of 2 interdigital transducers that we lithographically pattern on the surface of a lithium niobate, in this case, crystal. For these particular experiments, these IDTs were designed to operate at around 330 megahertz frequency, but the acoustic frequency can actually span quite broad frequency range, from few megahertz to several tens of gigahertz here. And this can be achieved simply by changing the design and the size of these IDTs. So the reason why we use highly piezoelectric substrates is because in that case, we can obtain a strong strain and piezoelectric fields. And then we can use both of those fields to dynamically control optical, electronic, and mechanical properties of semiconductor structures, as we previously reported in 3-nitride and 3-arsenide quantum dot systems. So what we then did is we deposited along this acoustic propagation path in between the 2 IDTs, either 3-nitride nanowires here, which we previously mechanically removed from the native substrate, or thermally expanded hexagonal boron nitride flakes. And in both cases, as seen in the optical microscopy images, we can find regions with low density of these structures, so we can analyze then the luminescence of single structures simply by direct optical illumination by a focused laser beam. So let's first see the results that we obtain in 3-nitride nanowire quantum dots. So what I show here is a typical low temperature microphotoluminescence spectrum, which is recorded on individual nanowires. So this is a confocal, actually homemade micro-PL system. And as you can see, this spectrum exhibits 4 different emission bands. This highest energy emission comes from the near band edge luminescence that originates from the gallium nitride nanowire body here. These other 3 emissions are due to the indium gallium nitride contributions. So basically, they come from this top polar here, this one, then side semipolar, this one here, and the non-polar lateral facet here. So the reason why there is an energetic shift between these 3 bands is, of course, because each facet has a different indium content. Also, as I mentioned before, different value of the built-in electric field, and also because, as you can see, the thickness of this nanoshell is different and depends on the facet orientation. So we also observed, as you can see here, the presence of such intense and sharp emission lines, which are superimposed on the overall emission band. We can observe some of these lines up to some 80 Kelvin. At low temperature, they have a line of about 300 to 700 micro EVs, which is not so bad. So we basically attribute the presence of these lines to the exciton localizing potentials, which are induced by random fluctuation of indium content across this intra-wire InGaN nanoshell. So basically, there is a clustering of indium inside the indium gallium nitride nanoshell, and this clustering acts as a quantum dot confinement potential, which is optically active and is able to emit single photons. So we then performed the polarization resolved micro-PL characterization for each type of quantum dots, meaning polar, semipolar, and non-polar. We just randomly chose some wires and some quantum dots formed on those facets. As you can see, they all have a highly linearly polarized light emission with the degree of linear polarization above 75%. So this is quite high degree of linear polarization, which, as I have mentioned before, is important in order to be able to encode information onto the photon polarization state. Now, such high degree of linear polarization can be ascribed to a particular anisotropic structure of the quantum dot confinement potential concerning both the shape of this quantum dot potential and also the presence of strain inside the heterostructure, as it was previously reported in other polar as well as non-polar InGaN quantum dots. Now, what we then wanted to do is to ensure that we are really dealing with quantum light. For that, we basically filter out the emission of a nanowire quantum dot using just a single grating spectrometer, and then signal is then sent to the Humbury, Brown, and Twist interferometer, which, for those who are not familiar, consists of a beam splitter and 2 single photon detectors positioned in the reflection and transmission arm of this 50-50 beam splitter. So the signal of these from these detectors is then fed into the electronics, which delivers such histograms of correlation events as a function of time delay for the consecutive photon detection at both detectors. These histograms are proportional to the second order correlation function. And in the case of truly single photon emitter, what we expect to see is that this G20 is completely vanished here at 0 time delay. And this is because if we send a single photon to this beam splitter, it cannot divide itself, so we cannot obtain simultaneously, in the case of single photon, counts at both detectors. Right. So indeed, if we perform these measurements on quantum dots of each crystallographic orientation, so we do see such reduction of coincidence rate at 0 time delay. So here and here, so for polar, semipolar, and non-polar dots. And this basically shows that we are indeed dealing with anti-bunched light emission. So the reason why this coincidence rate in all three cases is not going completely down to zero is because we have here some background photons, which are also collected by the system, and also because the system has a limited temporal resolution. So if we correct these measurements for both background photons and limited time resolution of our measurement system, then the G2 values at 0 time delay, as you can see written here, goes well below the 0.52 photon threshold in the case of two independent quantum emitters. And this is a clear signature of single photon emission from nanowire quantum dots. So we also performed time-resolved micro-PL experiments, and as expected, we observed that semi-polar and non-polar quantum dots indeed exhibit much faster recombination rate compared to the polar ones. And this is, of course, because the built-in electric field and therefore quantum confined Stark effect is basically absent on these low polarity planes, as we expected. Now, in order to show what happens when we apply the acoustic wave to these nanowire quantum dots, I will focus on the quantum dots in this polar topmost region of the nanowire, but we basically observe the same results for semi-polar and nanopolar quantum dots. So what I show here is just a low temperature micro-PL spectrum recorded on one of these nanowire quantum dots. And you see that it exhibits, again, such very narrow lines, which correspond to the recombination of the excitonic complexes, including an exciton and biexciton, originating from one of these optically probed nanowire quantum dots. So this exciton-biexciton assignment here is corroborated by the excitation power dependence measurements, which, as you can see here, shows such linear for the case of exciton and quadratic for the case of biexciton increase of the integrated peak intensities as a function of optical pump power. Additional confirmation is provided by polarization resolved experiments, and they show that these two lines are collinearly polarized, as you can see here, and they exhibit the same degree of linear polarization, what we actually expect in the case when exciton and biexciton are emitted from the same quantum dot potential. So when we apply the acoustic wave now, what we observe is that these excitonic lines split, and we see that the magnitude of this splitting increases continuously as we increase the amplitude of the acoustic wave, meaning the RF power that we apply to the IDTs. And this, the bandwidth of this splitting can reach some 2 millielectron volts for the highest possible acoustic amplitude. So there's a limit actually of the RF power we can apply to IDTs so that we don't break them, which is around 26 dBm in our experiments. So these experiments actually, or these results actually show that the acoustic wave can be used to tune spectrally the quantum dot emission. And this is an important result because, as I mentioned before, with this, we are basically able to address the challenge of having indistinguishable photons. So by applying the acoustic wave, we can affect the similar quantum dots and force them to have identical emission wavelength as long as their emission energy is within the approachable bandwidth here. So the observed spectral changes can be attributed to the periodic shifts, as you can see here, of the quantum dot energy levels, which are induced by deformation potential coupling between this emitting state and the acoustically driven mechanical vibration or strain. In other words, as the acoustic wave propagates and couples to the nanowire, the embedded quantum dot is dynamically strained, and its transition energy is sinusoidally modulated so that it oscillates between a minimum and maximum value with respect to this equilibrium energy in the absence of the acoustic wave. This is also very well observed in stroboscopic time-resolved micro-PL experiments performed under pulsed optical excitation synchronized with the acoustic wave, where you can actually see such sinusoidal oscillation of the transition energy during the decay. Now, if we integrate this over time, we obtain such apparent splitting of the PN lines. And in this context, this minimum and maximum transition energies correspond to the acoustic phases at which the tensile and compressive strain have the maximum value. So in addition, we can now use this ability of the acoustic wave to induce such fine spectral tuning of the quantum dot transition energies. And we can basically combine it with spectral filtering in order to control the photon emission time. This can be done simply by collecting the photons in a narrow wavelength range here. So if, for example, we would collect the photons at this maximum or minimum energy of this acoustically driven spectral modulation, we would see that these two emissions are out of phase with each other and that the photons are emitted at the acoustic frequency. If, on the contrary, we collect the photons at this equilibrium central energy here, the emission will take place twice per acoustic frequency, at twice the acoustic frequency. This is because the emitting states, as you can see by these marks here, moves past this energy twice per acoustic cycle. So in this way, we can control acoustically the photon emission time. This was already observed previously for other 3-5 quantum dot systems. And the advantage of this method is that we can produce and manipulate on demand quantum light states over a much broader frequency range as compared to other schemes. We can go up to tens of gigahertz frequencies. And also one of the main advantages is that the jitter in the photon emission time is significantly reduced, which is quite important for practical applications. So we don't actually need to use anymore the pulsed laser in order to obtain on-demand single photon emission. So now we came to the idea after the previous experiment that we can apply, instead of sinusoidal voltage to the IDTs, a different signal with specific waveform that we can actually design. So if we do that, the same as what you have seen previously, our nanowire quantum dot will act as a sensor, meaning that this acoustically driven fine spectral tuning will exactly follow the form of this driving signal that we apply to the IDT. So if we now combine this with spectral filtering, we can therefore obtain much more complex temporal sequence of the emitted photons. So one example is shown here. So now we see that there is a specific frequency of the photon emission time. So they are not equidistantly separated in time anymore. So now, for example, we can select at this energy the photons, in which case we obtain different time sequence, of course. So these time sequences of the emitting single photons is basically mediated by filtering the light at different energies of this acoustically induced fine spectral tuning. So this is quite useful for obtaining time bin encoding. So which basically, by playing with this waveform, we can obtain all possible options for time bin encoding, meaning long, 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 short, 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 and short, long. So actually, with this time bin encoding, as I mentioned before, we can make a much more robust system because it's quite robust against decoherence and it's better suited to be used in fiber optics as, for example, polarization encoded. So this is actually very important for telecommunications or quantum communication in the future. So we can basically, if we achieve emission of single photons in the telecommunication wavelength range, then using this simple method, we can basically use the existing telecommunication infrastructure for quantum information communication. So we have also seen that using our acoustic waves, we can tailor the initially high polarization degree of the emitted photons, either from exciton or from bi-exciton. So here I showed the example of the exciton. And as you can see here, at the acoustic phases at which the transition energy of the exciton has the minimum or maximum value, we observe such reduction of the polarization degree up to some 30%. So we are basically limited here by the maximum acoustic power that we can apply to the IDT. Otherwise, we could go even further. Now, there is a theoretical prediction made by other authors, which basically shows that in trinitride word-side quantum dots with internal anisotropy, any change in spin-orbit coupling, or basically in valence band mixing, we can lead to significant change in the polarization degree, as you can see here. And this change can be obtained by applying externally either strain or electric field, such as that of our surface acoustic wave. So basically, either strain or piezoelectric field, or both of our propagating acoustic wave, can be responsible for this reduction of the polarization degree. So the strain field alone actually cannot be responsible for this reduction of the polarization degree of the emitted photons. And that is because, based on a theoretical calculation here, the actual strain that we would need to obtain such a range of change in the photon polarization degree, well, this one here, is an order of magnitude larger than the maximum value of strain that we can obtain with the acoustic wave. And also for anisotropic quantum dots, such as those that we have in our nanowires, the tensile and compressive strain is expected to produce changes in the polarization degree of opposite slope, which is not what we obviously observe here. So we basically attribute this reduction of the polarization degree to the effect of the acoustic piezoelectric field. And the underlying mechanism is that the piezoelectric field is tuning the spin orbit energy and thereby affecting by that the polarization degree. So this tunability of the spin orbit coupling by externally applied electric field was previously seen in other quantum dot systems, such as indium arsenide. This was an experimental observation. And it was also theoretically predicted for word-side trinitride quantum dots, where it has been shown that by applying static electric field up to some 200 kilovolts per centimeter, we can indeed obtain such change in the polarization degree between 0 and 80% of the emitted photons. Now, it is therefore quite expected that the component of the acoustic piezoelectric field that is parallel to the nanowire quantum dot anisotropy plane and whose value can reach some few tenths of kilovolts per centimeter can indeed be used to change the photon polarization state. In this case, the change in the degree of linear polarization, as we observe here, is completely independent on the field orientation. What is important is that this field is parallel to the quantum dot anisotropy plane. And we also confirm that the origin of this behavior is due to the acoustic piezoelectric field by performing such experiment where we looked at the polar nanowire quantum dots in the absence of the acoustic wave. And then we see that when we apply the laser excitation power while increasing this optical pumping, we are screening the built-in electric field which exists in polar quantum dots. And this screening of the built-in field by photo-generated carriers leads to the reduction of the spin orbit energy, and thus to increase of the polarization degree. Now, the fact that we don't observe this effect in non-polar and semi-polar quantum dot indeed suggests that it is the piezoelectric field that is causing this behavior. With this, we can pass to, and this is just a brief description because it's quite similar to the previous, to a different type of sample, which are atomic defects in hexagonal boron nitride flakes. We have also performed similar experiments in different 2D materials like tungsten diselenide, molybdenum disulfide, etc. And we can basically obtain similar results. So in the case of HBN flakes, which are transferred onto silicon dioxide substrate here, using the same confocal micro-PL setup, we observe at low temperature such PL spectrum. And as you can see, there are many these sharp and intense lines here, and they span a very broad range from some 450 or even below nanometers to some 700 nanometers. Now, the line width of these peaks is around 1.5 milli-electron volt at low temperature. And some of these lines are observed even at room temperature, with, of course, expected PL quenching and line width broadening. Now, many experiments in different groups on hexagonal boron nitride monolayer, multi-layer flakes, as well as crystal, have seen such sharp lines, and they are attributed to the zero phonon line emission coming from atomic defects that can confine energy levels deep within the band gap, and they can act, as I've commented before, as recombination centers for the emission of single photons. Now, I also mentioned that it is still not very clear which is the actual chemical structure of the defects that are causing such sharp emission lines. But we recently performed a DFT calculation. I think the T is missing here, so sorry for that. Which basically shows that the defect that is giving such sharp emission lines is most probably the nitrogen and anti-site vacancy. And this is also reported by some other authors who performed similar research, and they also came to the similar conclusion that the actual structure or atomic defect that emits single photons in HBN system is nitrogen anti-site vacancy. So we also wanted to check what is the polarization of these PL lines, because as I mentioned, this is important for polarization and coordinate protocols. So we randomly choose some of these lines at different energies, and we saw that they indeed are highly linearly polarized with a degree above 85%. The fact that the random defects have actually intrinsic orientation, as you can see here, of the polarization axis, suggests that this high degree of linear polarization is due to the anisotropic structure of particular emitting defect, which actually are electrical dipoles. So what we then also wanted to prove is that we again have single photon emission from this system, and we used, as I said before, Humphrey-Brown and Twist interferometer, and we see that even at room temperature, most of these lines coming from the atomic defects, do actually show such reduction of coincidence rate at 0 time delay, And when we perform the correction for the background and temporal resolution of our system, we again obtain the G20 values, which are well below this 0.5 threshold. So this means that these atomic defects in HBN layers are indeed emitted single photons. So now when we apply the acoustic wave to these atomic defects, what we see is that some of the lines also exhibit such apparent splitting, as you can see here. And this splitting also increases as we increase the acoustic power. You see here that as opposed to nanowire quantum dots, at higher RF powers, there are some non-linearities that are appearing, and they probably come from a slight decoupling of the flake from the substrate. And this can basically lead to, or this can basically be induced by a slight rotation of the flake, or by slippage among different layers within the flake. But the fact that not all emission lines are affected by the acoustic wave basically shows that not all defects have equally strong mechanical coupling to the substrate. So what we actually need is to have a strongly coupled defect to the substrate in order to observe such behavior. And we then, for some future experiments, plan to encapsulate these grains or HBN flakes into some transparent piezoelectric material so that we could improve the coupling and actually get single photon emission affected by the acoustic wave for all cases, which is important for practical applications, of course. So our results show that the energy shift of the defect emission that is now shown here, again, actually is around 50 millielectron volts per percentage of strain. And this is an order of magnitude higher than previously obtained results by other authors who observed in multi-layer hexagonal boron nitride flakes different coefficients around, let's say, maximum 6 millielectron volts per percentage of strain when they apply static strain to this HBN flake. So such high elasticity of hexagonal boron nitride that we have obtained is actually an indication that we can use strain engineering to tune the optical properties of quantum emitters within our HBN defects. So this is quite relevant for the implementation of these emitters into future and existing photonic and optoelectronic devices. Also, if we go back here, now knowing that this strain tuning coefficient in the case of HBN material is quite large, this can also explain this large spread of these emitting peaks. So basically, only a small amount of strain is already sufficient to shift by quite large amount energetically these PL lines. So it really is feasible that the optical emission resulting in single photons really comes from a particular defect species, as it was shown by the FT calculation. So basically nitrogen anti-site vacancy. And so this basically brings me to the summary. So what I have shown here is that we can generate single photons, which are highly linearly polarized, using trinitride core shell nanowire quantum dots, and also using atomic defects in HBN flakes. And we have also seen that these emitted photons are quite sensitive to the propagating acoustic waves, and that this can be used to control in situ the photon emission wavelength, its emission time. We can also control the photon polarization degree and encode information by time binning. So all these functionalities here are important for the implementation of such systems into future polarization based, but also time bin encoding on-chip quantum information processing. So with this, I would just like to acknowledge the actual support from the Spanish ministry throughout these national projects here, and also NATO, who partially also finance this research. I would also like to thank other colleagues from the Complutense University in Madrid. They performed the TEM characterization that I showed previously, and also our colleagues from the Paul Rood Institute in Berlin, who provided us with the acoustic delay line that we used for acoustic experiments. And with this, I would like to thank you for your attention.
Thank you, Snežana, for this nice talk about these very complex photonic systems. So if someone have a question, so be free to ask.
Thanks very much for the very interesting talk. I had a question about the hexagonal boron nitride. So you've got this really rich photoemission spectrum coming from that. And you mentioned that some of the bands come from defects within the lattice. I just wondered how many of those bands could come from the edge of the flakes.
Can you repeat the last part, sorry?
Yeah, I wondered if any of those emission bands can be assigned to the edges of the flakes.
Yeah, in the case of hexagonal boron nitride, that's not so relevant. We actually checked that, but in some other 2D materials, like for example, tungsten diselenide or germanium selenide, for example, sorry, gallium selenide, this indeed is the case, because there we actually have a paper published. We can strain engineer the quantum emitters. So because at the edge of the flake, there's a different strain gradient, sometimes we can also observe that the emission comes from defects due to the presence of edge. But this is not actually happening in the case of hexagonal boron nitride, which basically indicates that it's probably not strain itself that produces these defects. So as you have seen, we try different methods. You can also do, the bombardment of the flake with some ions. People also do that to produce single photon emitters. But in the case of HBN here, it was only sufficient to do a thermal expansion at high temperature. And this already basically produced the defects. So it's probably due to some rearrangement of the chemical composition inside of the flake at high temperatures, or when we perform the bombardment. So not so much related to the strain engineering. Though it is true that once you have an atomic defect, of course, there will be different local conditions of the strain or electric field, and this will affect, of course, the emission energy, but it's not the actual cause of the atomic defects, to my knowledge.
Yeah, thanks very much. So you mentioned the Raman spectrum when you were showing the photoemission spectrum, right? You mentioned the Raman spectrum. So I just wonder if the actual Raman spectra gives you information about those defects.
We also try to see if there's well, in hexagonal boron nitride, actually, first of all, the number of layers does not change much optical properties, like in the case of some other 2Ds. So we also saw that if you measure, it's actually a good question, if you would measure at the edge or somewhere inside the flake, and if there is an effect of the strain, you would be able to see a shift of some of the Raman peaks. So that we also did not observe. So yeah, it pretty much indicates that the cause of this, or the origin of these atomic defects, is not strain related.
So thanks for the talk. I'm not a lot in the topic, but in the slide 28, 29, you show that the photon intensity was larger. Yeah, for the previous one, maybe it's easier. you mentioned that here the oscillation corresponds to the tensile and compressive strain, if I understood well.
Yeah, actually, this is the best seen here, right? So you can see here, this is the time resolved measurement. So if you would do it without the acoustic wave, you would just see the exponential decay, let's say mono-exponential decay of an exciton or bi-exciton complex. But when you apply the acoustic wave, then during this decay, what you see is that the transition energy is really modulating sinusoidally, because the signal that we apply to the IDT has a sinusoidal form, right? So then what I showed here, so this splitting of the line is actually what we obtained from this when we integrate this over time, and then we get this apparent splitting. So what actually happens is this here, that during the decay, when acoustic wave is applied, the strain or the deformation potential coupling is what causes this modulation of the optical transition energy. So it oscillates sinusoidally like this.
But then in the next slide, here or here, you see that the intensity is larger for particular strain states then.
Oh yeah, this is different.
These red dots here.
Yeah, this is different. So because this, what we have done here, you see, this is time decay. So it's this is a time resolved detection, right? But what we did here is we used pulse excitation, but this was time integrated detection. So in this case, you can actually track, and this is only in the case of the bi-exciton because it has actually, I think I have some transparencies. Let's try to find it that can explain it better. Prepared. Maybe go. I think probably, yeah, well, here. Here you can see, okay. So this is what you get from an exciton and bi-exciton when no acoustic wave is applied. So that's basically the decay. And then on the transparency, I showed before that if you apply the acoustic wave, you would see those sinusoidal oscillations, right, during decay. Now, obviously, we have a different lifetime in the case of exciton and bi-exciton. So bi-exciton has almost approximately half of the lifetime compared to the exciton. So then, depending on the lifetime, we can basically see such oscillations when we perform the time integrated detection. So the difference was that in this case, we have time integrated detection, and the other case was time resolved, right? This we cannot see in the case of the exciton because it has a long lifetime. So basically, this modulation is kind of smeared out. So it's only we can only observe it for those transitions which have the lifetime that is shorter, basically, than the acoustic period. So that's the difference. In one case, we have time resolved detection. In another case, we have time integrated detection. But in both cases, the excitation is pulsed, and it's synchronized with the acoustic wave.
Thank you.
Somebody else?
At the end, you mentioned that some of the effects that you see when increasing power in the acoustic wave could be due to the rotation of the flake. Okay, is this a pure mechanical effect, or there is some thermal effects also because you are heating more?
It's actually a reversible effect. It's pure mechanical effect because we could see while measuring, while doing the experiments, that we have the splitting. If, let's say, if we are measuring time integrated just with the CCD camera, so we see this apparent splitting of the PN line, and then suddenly we don't see it anymore. And then while we apply the acoustic wave. And then if we would stop applying the acoustic wave, after some time, it would again appear. So it seems that basically there's a slight rotation of the flake due to the propagation of the acoustic wave. But once the flake, the wave is not propagating, it typically can go back to the initial conditions. Yeah, so it's just mechanical effect.
Okay, in the case of the nanowires, if I understood correctly, you have 3 different photon emitters, and well, one is in the top and the others. Is it just due to the geometrical form, or is it related to the crystallography inside the nanowire?
Well, it's so in molecular beam epitaxy growth, the growth conditions really depend on many parameters. So like what is the temperature, for example, what is the ratio of the nitrogen flux compared to indium or gallium in that case, in this case. But it also depends on what is the crystallographic orientation on which one grows. So the growth dynamics significantly changes depending on the orientation. This is simply because of the different chemistry that is involved. So that means that in our case, and we actually confirmed it by dispersive electron X-ray measurements, we see that the indium incorporation rate is the highest when we grow on polar C plane. And then it reduces for the semipolar, and it's even less on the non-polar. So that's first of all that. So there's different content of indium or different concentration of indium on different planes. And of course, if you add more indium, then the emission shifts. And also because of different dynamics of the growth, the growth rate or velocity is going to be different for each orientation, which is why we can have, or we observed actually thicker InGaN layer on the polar plane, because the growth is faster there than compared to the, let's say, non-polar, where it's slower. So it really depends on the chemistry and the conditions that we use during the MB growth.
And then when you deposit these nanowires on top of the acoustic wave, I guess the mechanical connection is better than in the flakes, because you have the splitting in the 2 lines.
Well, the mechanical connection between the whatever is the emitter and the substrate, of course, it's a complicated topic. So, like, if you remember, there's this pyramidal top of the nanowires, and the quantum dot is actually positioned in this pyramidal top. So if the pyramidal top is not really touching the substrate, then the mechanical coupling is not so good. Yeah? So we observed that in the case of nanowires, which is why we also then performed a similar experiment, but we encapsulated everything with polycrystalline zinc oxide done with RF sputtering at room temperature, not to damage the IDTs. And in that case, the coupling was perfect. So all possible quantum dots that we could find in every nanowire was affected by the acoustic wave. So the same occurs with the flakes, because when you disperse the flakes, it's very difficult to disperse them so they are completely individual and very well oriented. So the coupling is also random. But the best way to basically achieve that the maximum coupling of the entire system is by encapsulation into some piezoelectric but transparent material. And just to go back to your previous question, sorry. So in this case, we designed the conditions of the growth, MBE growth, so that we can obtain such structure. But it doesn't have to be like that. One can use different parameters during the epitaxial growth. So we can have nanowires, which, for example, have top profile. So this really depends on the design and the parameters we use. So that's a study on its own. Yeah.
Thank you.
We don't see.
No.
Yeah.
Okay.
No. Okay.
So I would like to thank Snežana again.
Thank you very much.